Good morning, my YouTube viewers. It is Crystal here, and what I wanted to talk to you about in this video is experimental design. Experimental design is another concept that is used in statistics, and so that's what I wanted to discuss. Statistical experimental design forms the backbone of empirical research, providing a systematic approach to investigating cause and effect relationships. Its methodology ensures that researchers can draw valid conclusions, minimize bias, and effectively allocate resources. The process for conducting experimental research is 1. Define the research objectives. 2. Design research methodology. 3. Conduct a thorough literature review. 4. Develop a research design. 5. Collect and analyze data. And 6. Present empirical findings. And then so what we're going to do is we're going to be talking about different ways that you can carry out experimental design in your statistical work, but I'm going to have to do it in different videos because it's a lot to cover. So the first method of experimental design that you can use is single factor completely randomized design. So experimental units are randomly assigned to all treatments, making this design simple and effective when variability among units is minimal. So we've got an example that we're going to review the code for. So you're going to have 3 fertilizer treatments applied to plants and randomly assigned. So the factor is going to be the fertilizer, F1, F2, and F3. So the response is going to be plant growth. So your null hypothesis is no significant effect on plant growth, and your alternate hypothesis is a significant effect on plant growth. So we're going to go through a program that utilizes completely randomized design with one factor being the fertilizer. Fertilizer is the one factor. So the first thing that you want to do is you want to set your seed. And what happens when you set your seed is every time you run the program, the variables will initialize to the same values. So you type set.seed brackets 1, 2, 3, and then you can type any number you want within the brackets. Now we're going to set up the factor levels. So fert becomes factor, brackets, repetition, that's a vector, brackets, C, that's a vector. So within C, your vector, you've got 1, 2, 3, and each element has 20 elements. So that means you're going to have 20 F1s, 20 F2s, and 20 F3s. So we're going to simulate the growth data, and we're going to simulate it with different means. And so this is simulated data that we're creating, okay? So we're going to carry out growth becomes C, that's a vector. And then F1 is going to be a randomly sampled normal distribution of 20 samples with a mean of 15 and a standard deviation of 3, comma. F2 is a randomly sampled normal distribution with 20 samples, a mean of 18, and a standard deviation of 3, comma. F3 is a randomly sampled normal distribution of 20 samples with a mean of 20 and a standard deviation of 3. Okay, so you can see here that this sample data we're creating is F1 has a mean of 15, F2 has a mean of 18, and F3 has a mean of 20. But in real life, you don't know what the mean is going to be. But this is just the data that we've created to demonstrate this program. So dat becomes data.frame. So you're creating a data frame. brackets fert, that's your fert, which is the F1, F2, F3 of 20 each, and then growth. So, and that's going to be the F1, F2, F3 as well. And then so we're going to look at the head of data. So when you type head of data, what that does is that allows you to see the first 6 rows. So we've got the head of data. So that's F1. So what that's telling you is the first 20 is F1, the second 20 is F2, and the last 20 is F3. So you're just seeing that you've got your fertilizer and you've got your growth. Okay, and so the growth is going to be, I guess it's going to be checking the means. So now we're going to do a one-way ANOVA, and this ANOVA that we're going to be using is going to be within a linear regression model. And the reason why is because R has 2 types of ANOVA. One ANOVA is within a hypothesis test, and the second ANOVA is with a linear regression model. And so we're using the linear regression model. So fit becomes AOV brackets growth tilde fertilizer fert, comma data equals dat. So growth is your y variable and fert is your x variable. And then we're going to type a summary of the fit so you can see what the summary of this is, of this ANOVA is. So this is a summary. So you've got the degree of freedom is 2. And you calculate the degree of freedom by the number of samples is 3. And you subtract 1 from the number of samples, and that's 2. Then it gives you the sum of squares, the mean square, your F value, and your P value. So the P value is a very low value. And then you've got your residuals. And the residuals for the degree of freedom is going to be the number of elements, which is 60, and then subtract 3 from that because that's the number of samples. So 60 minus 3 equals 57. You've got your sum of squares and then your mean square. And then you've got your significant codes as well. So that's giving you the output of the ANOVA within a linear regression model. Now what we're going to do is we're going to plot this on a chart. We're going to make box plots with group means and 95% CI, which is confidence interval. So you're going to create a box plot, brackets, growth, tilde, SAR, that's your linear regression model, data equals dat, comma, color is a vector of steel blue, tomato, and gold. Main is the title of your chart, which is completely randomized design, fertilizer effect. XLab is a label on the x-axis, which is fertilizer, and YLab is a label on the y-axis, which is plant growth. And then we're going to add the group means. So group means becomes T apply, brackets, dat, $ growth, comma, dat, $ fert, comma, mean. And so your points, you're going to put some points in this chart, brackets 1 to 3, comma, group means, comma, PCH equals 19, comma, color equals black, comma, CEX equals 1.4. Now we're going to add the 95% confidence interval for each group. Group SD becomes T apply, brackets, dat, $ growth, comma, dat, $ fert, comma, SD. And SD stands for standard deviation. N becomes 20, that's your number of samples. And then CI lower becomes group means minus 1.96 times groups XC divided by square root of N. CI upper becomes group means plus 1.96 times group SD divided by square root of N. We're going to put some arrows in the chart. And so your arrows is brackets 1 to 3, comma, CI lower, comma, 1 to 3, comma, CI upper, comma, angle equals 90, comma, code equals 3, comma, length equals 0.08, and line width equals 2. Now we're going to do some diagnostics. So the ANOVA diagnostics are PAR brackets MF row equals a vector of 1 and 2. Then you're going to plot brackets fit, comma, which equals 1. So that's your residuals versus your fitted. And then plot brackets fit, comma, which equals 2. And that's a normal QQ plot. And then PAR brackets MF row equals a vector of 1, comma, 1. So we're going to come down here, rerun our program. So this is the box plot that we created, and so you can see that the p-value is 3.82 to the neg 6. So you can see that the p-value is really low. It's lower than the significance level of 0.05, which is normally what people identify as being significance level. It can go up to 0.1 and it can go all the way down to 0.01, but most people use 0.05. And since it's lower than the significance level of 0.05, you can see that they're going to reject the hypothesis in favor of the alternate hypothesis. So the null hypothesis is there's no significant difference between the means, and the alternate hypothesis is there is significant difference between the means. So we're accepting the alternate hypothesis, saying that there is a significant difference between the means. And so we've calculated the box plots for F1, F2, and F3, and then you've got the first quartile and your third quartile are the bottom and the top of the box. The second quartile is the line in the middle of the box, and the mean is the dot. And as you can see, the mean is not always on the second quartile, and so that's important to know, because the mean is calculated as the sum of the total elements divided by the number of elements. And the median, which is your second quartile, is going to be the middle of the elements. So you've got 20 elements, so the second quartile is going to be the middle of that, like element number 10. And then there's also different ways that you calculate elements, calculate the medians. So if the number of elements in the data set or number of sample is an odd number, then what you do is you take the middle element, and that is your median. But if the number of elements in the sample is an even number, then you take the two middle elements, you add those elements together, and you divide those elements by 2, and that's going to give you your median. So that's telling you that there's two ways you have to calculate the median depending upon whether the sample has an odd number of elements in it or an even number of elements in it. And as you can see, you've got whiskers. So the bottom whisker is going to be F0, and the top whisker is going to be F4. So you've got whiskers on your box plot as well. So the whiskers identify the outliers. And so what that's telling us is that F3 gives you the greatest plant growth, but that's because we have simulated the data. But in real life, you don't know what it's going to be. But this is just an exercise. And then the next thing we do after we do the box plot, we also do the diagnostics. So you've got your residual versus your fitted, and then you've got your QQ residuals. So a QQ plot is a quantile plot. And so since these dots on the QQ residual fall on the regression line, and the regression line is of a normal distribution, then you can see that this is a normal distribution, which is what we've already created, because when we created the growth, we used a randomly sampled normal distribution. So this is just sample data that we have used. And so that concludes this video on this single factor, completely randomized design. The next video, we're going to be covering another type of experimental design, and I hope that you decide to watch it, and I hope you've got something out of this video. Thank you for watching.